Thanks for the introduction, and also thank you for the invitations. I very much enjoyed my stays, and I learned a lot from the other talks. So as you can tell from these titles, it is kind of related to the theme of this workshop, but not directly. But I hope when I finish my talk, I can see the essential connection between these two. So essentially, my research work mainly focuses on the multi-scale modeling of kind of multi-physics systems. So this work is devoted to learning the closure models for the polymer fluid, but you can see that essentially we share the similar challenge when we switch to the topic of charge fluid, right? So there's some kind of closure relevant to the micro-scale physics. And what I'm interested is trying to use machine learning to learn some macro-scale models that inherit the micro-scale physical law. So that is my major interest. Okay, so let's start. So I'm going to start with some background information about what is non-Newtonian fluid and what is the challenge. And then I'm going to introduce a pathway to learn the macro-scale hydrodynamic models that ensure the energy stabilities, and on the other hand, strictly preserve the physical constraint, and also directly inherit the micro-scale physical law. So that will be the three features we aim to capture. And then I'm going to show you some numerical result with some open problems relevant to this direction. And hopefully we can establish some connections with the charge fluid, which is the theme topics of this workshop. Okay. So what is non-Newtonian fluids? So essentially on the micro scales, non-Newtonian fluids are basically kind of polymer solutions. Okay. So here, the little ones can represent small solvent like waters. But on the other hand, we also have the big molecule, that's green ones, that represents the kind of like a polymer molecules. Okay, so it's quite common for our daily life, like the hand soap we wash hands since the COVID pandemic, right? And on the macro scales, these hydrodynamic models takes these general forms where U is the fluid velocities, okay, rho is the densities, P is the pressure arising from the incompressible conditions. And now this tau represents microscale interaction, okay, essentially the stress, okay? And this, from a modern perspective, this is the terms that all this challenge comes from, okay? So specifically, for small molecules, okay, like waters, okay, so the typical relaxation time is very small, okay, compared with the hydrodynamic scale. So we have a closed form for the solvent stress term. This is just Newton's formulation, right? However, we do not have such a simple closure equations for the polymer stress. In particular, for the polymer molecules, the typical relaxation times could be very long, could even comparable with the hydrodynamic scales. And as a result, because we do not have such a time scale separation, okay, we do not have this kind of simple, like the upscaling or homogenization or other kind of simple closures. And that's why we do not have an analytical form for this tau p. And that is where the challenge comes from. And this is, okay, so the whole topic we're devoted to how to learn this tau p, okay, for the macro scales, while on the same time ensure the mathematical structure, okay. But before we start, so I always like a simple problem, okay? So we're dealing with a difficult, complex system, but I want to start some problem as simple as possible. So one simple thing is just the one-dimensional chain. So that could be very simple, right? Everyone learns this from the ODE course for undergraduate. So this is just a one-dimensional chain. Okay, so the system is linear, very simple, right? Okay, now I ask the question, what about if we are not interested in a single blue particles, but instead we're interested in coarse-grained particles, like this one. Here, this green particles is nothing but just a group of multiple blue particles, small particles. So now I want to ask the question, if we do this upscaling, what is the equation of motion for the green particles? In particular, on the micro scales, it is just simple, very linear, okay, deterministic. Now, what about this one, the big ones? Is it still like this or not? So that would be the question, okay?
You want us to guess? Are you waiting for us to guess?
Whoa.
No, I say no.
It's simple. No, you guess. So.
I guess no way.
No way.
I don't say no, I say no way.
So, which means that, right? So it's just and just some. Okay, so it's simple, right? So this is just the you see, there's no free lunch. If we do this scale upscaling, we drop this variable y, then the price we need to pay is that the equation of motion for the x, becomes complicated. Becomes there's a memory terms comes in. So that's just a very simple example to make an analog why the system becomes complicated if we do this upscaling. And we can see that only if there's this epsilon approaches zeros, then we have a scale separation. And if this is true, then the system becomes deterministic. There's no kind of like a memory effect. So that's just a simple analog. Okay? So go back to our problem. So what does it mean? So essentially, on a macro scale, so the polymer stress is determined by micro scale molecular interaction. Right? So here, say we use the Kirkwood formulation, right? So here is the R is basically the bound vectors, and the V is the micro scale potential functions. Okay? Then in principle, we can write out the polymer stress tau P in terms of the micro scale interaction, in terms of this V, right? So in principle, it is determined by this V, and also the little f represents the distribution function of the polymer configuration, essentially the bound vectors. Okay? So in other words, if we know this PDF, the distribution functions, then we should be able to know the polymer stress. However, that's where the challenge comes from. It will be very difficult to predict or compute the probability density function of the polymer configuration, especially the time dependent, right? So that's essentially, as you can see that tracking the density distribution function of polymer becomes computationally very expensive. Essentially, it is essentially equivalent to solving this Fock-Planck equation, and it becomes computationally, I would say, prohibited if this polymer configuration becomes large, right? So let's say you have complex polymers. The R is not three-dimensional. It could be very easy to go to hundreds of dimensions. Then we are not able to directly track this PDF, and that's where the challenge comes from. Okay? So with that, so what do we do? So usually, to close the systems, we introduce some kind of empirical closures. Assume that this polymer stress tau P is a function of C. And this C is basically some kind of like a orientation tensor, usually the second order moment, in terms of this F, that characterizes the microscale, the polymer configurations. So here, usually, one way is just take the standard of the second moment. And once we have these, right, so we assume that the polymer stress is a function of C. And then, in order to track the dynamics, we also need to model the time evolution of this C, the orientation tensor. We assume that the time evolution dc dt equals to hc. So which means that we have to introduce another empirical closures for this dynamics of C. So again, we have the two empirical, right? So function G and H. But that's not enough. Even for the left-hand side, you see here, this one, dc dt. This is the so-called objective tensor derivative. I want to emphasize that even for these terms, it has to satisfy some kind of the so-called frame indifferent constraint. What does it mean? It means that for the same systems, if we observe the evolutions in two frames, while the second one is rotating with respect to the first one, then we should get the same physical law. And because of this invariant frame indifferent constraint, so we have to ensure that this dc dt must satisfy this constraint. And mathematically, in order to do this, so there's not a unique way. We can have a lot of choice. For example, the upper convective, lower convective, co-rotational. Actually, we have infinite number of choice, okay, to impose this the frame different constraint. So that's another thing we should keep in mind. So, okay, let's give a simple example. What does it mean? So, in particular, if we just consider that we have consider a dumbbell molecule, the simple ones, okay, just have like one we have molecule that is characterized like dumbbells, okay, and R is like this, and we assume that the interaction is quadratic, okay. So if we assume V is quadratic, then the polymer stress, you can see that it now becomes very simple. Okay? It's basically R and R transpose, and that is essentially C, which means that for this simple case, this tau p can be closed by C. And accordingly, the evolutions can be also take these very simple systems. Okay, this is the left hand side dCdt, and this is HC. And this is the so-called Hawkins model. Okay. But in realities, the polymers could be takes a very complex structures, and also this V could be nonlinear, right? So we do not have such a simple closures for the systems we are interested. So intuitively, to track right the complex systems, we may want to introduce maybe perhaps one single this C, right? The second moment closure may not be sufficient. Maybe we should introduce multiple C's. Okay, but if we do so, each C will need its own object tensor derivatives and the closures intuitively, right? So that's something we have not talked about detail, but that's just a simple intuition. Okay, so this is what we propose. Okay, then we propose that from a micro scales, we want to learn a set of micro to macro features. Okay, this is essentially a set of encoder function. This encoder function will be used to capture the microscale polymer configuration, essentially a set of features, which is give us the C1, C2. This is kind of like the so-called generalized conformation tensors. Okay, essentially the features of the polymer configurations, and then we're going to use these features to approximate the polymer stress and their constitutive closures, okay, the dynamics. Okay, so that's the basic idea. And as you can see that, essentially, if we would just do it just a naive way, you have a high dimensional PDF. What we can do is that we choose this B, right, as the simple one, like the first order moment, second order moment, blah, blah, blah. We go to all the high order moment. In principle, we can recover F. But computationally, that's intractable, right? So that's something we should keep in mind. Okay, so to proceed, okay, we want to use machine learning to do this. However, I want to always start with something like the negative part. So machine learning definitely is very powerful these days, right? We have to do a lot of things to especially approximate high dimension function. But on the other hand, every time we want to say or propose that we want to use machine learning to do something, we should keep in mind the criticism. It also has acquired the reputation of being a set of black box trick, right? Many people criticize that there's no interpretation abilities for the machine learning. So that's something we should keep in mind. So if we propose to use machine learning, okay, to learn these closures, the first thing we want to ask is that how do we gonna pass the physical law across the scales? So especially if we want to learn some dynamic model, right? So are we really, okay, passing the physical laws across the scales? Are we really discovering something new, or we just rediscover something that has been discovered? Naively, we can think of like if we want to learn something like a dx dt equals fx. So for many cases, we can collect the time series samples of x, right? And then we'll get the time derivative for x, and then we use it to learn the right-hand side, dx dt equals fx. Okay, for many cases, we can learn it, or we can use machine learning to fit the right-hand side. That's not a problem. However, this may not be feasible, okay, if we really want to learn it from the micro scales. And why? Because the micro scale, the samples collected from the micro scale molecular dynamics simulations is often superimposed with the thermal fluctuation, right? So there's large statistical errors. So here is one example we collected from the micro scale MD simulations. So it's almost impossible to infer the correct time derivative from it. So which means that the right-hand side is not accurate if we want to deal with the time derivatives. Okay. And moreover, even if we have a supercomputer that enables us to collect the really large, high fidelity molecular dynamic simulations, as I mentioned earlier, right, we even do not know the left-hand side. So the dc/dt, from mathematical perspective, needs to satisfy the framing different constraint. However, we do not know from practice, we do not know which one is the correct one we should choose, right? We have the upcompacted, covariant, co-rotation, blah, blah, blah. We have infinite number of choices. But which one is the correct one we should pick if we want to fit with the left-hand side, okay? So another thing I think I believe is very important, but has not been, I think, frequently addressed when we talk about using machine learning to learn it, is that how do we ensure the numerical stability, okay, and also the generalization ability if we want to learn from dynamic system. For many cases, we've seen that we collected some samples from some kind of training set. Okay, we'll put it into a neural network. Okay, we'll learn the models. It looks fine to reproduce the result. However, first, we cannot guarantee it is stable, right? If we do really long simulation. And second, we cannot guarantee if we transfer it, let's say the model, to some other test set. Can we ensure that the model is still stable? For many cases, we do not talk about these issues at all. Okay, so that's something but I think from a scientific perspective, that's something we should keep in mind. Okay, so that's something, essentially what we aim to address, or at least partially addressed, for these non-Newtonian hydrodynamic models. I'm going to start with the macro models, how to ensure the energy stabilities. Okay, so here I propose a different pathway to do it. So let's start with this one, the micro scales, right? We have some kind of, let's say, the very high dimension Hamiltonian systems, Newton's law, and we want to construct the macro scale models. So basically, we have two pathways. So we have seen many cases that, start with the micro scales, we collect the samples, and then on the macro scales, on the PD levels, we assume that we are interested in certain kind of field variable, like a density, temperature, velocity, right? And then we assume that we're interested in this kind of variable chi, we call it chi, and then we use some black box learnings or couplings or kind of sparse identifications that help us to model the PDE forms, okay? And then once we learn the PDE forms, and then we choose various numerical method, okay, and discretize it to the PDEs. So that's one common way. But here, what I propose is a different pathway. Starting from the micro scales, okay, we want to learn a set of field variables, okay, as a kind of like encoders, right, as a function of the micro scales. And then instead of trying to fit the PDE forms, what I propose that we directly learn the variational form in terms of these variables. Okay, this kind of chi could again be the rho, the density, velocity, and the C conformation tensor that I mentioned earlier, right? So we assume that our macro model takes these variational forms. And once we have these variational forms, it automatically gives us the PD form. But the point is that if we start with this variational form, then we can directly discretize the variation structure, which directly gives us the discretized the PDEs, okay? So in another word, the original pathway is kind of like I would call it a construction or variation and then discretization. But here, what we did is first the construct and then variation. Okay, it's not kind of like a variation and construction. Okay, that which give us the PDE form. We got the construction in the variation formulation and then variation. Okay, and then discretization. So that's the difference. Okay, go ahead.
What is known ES?
Yeah, that's something I'm gonna explain. It's basically the energy and the entropy of the system.
Known or they learned?
It will be joint learned.
Okay.
Yeah, it will be learned. So that's something actually I'm going to talk about in the next slide. Okay. Okay, so that's exactly what you asked. Okay, what does it mean? So for a broad range of physics systems, I think for non-Newtonian fluid, right, for kinetic equations, and also actually for charged fluid, right, for many systems, it's essentially governed by a reversible and irreversible process. Okay, in this equation one, in form of equation one. This chi is the field variables, and then E is the energy, and S is the entropy. Okay, so the system, the evolution is governed by two processes. Well, here L is basically corresponding to the Poisson bracket, corresponding to the Hamiltonian structure, And then we have this M is a friction matrix that corresponds to a dissipation process. Okay, so essentially, these formulations go back to all the Ansak's reciprocal law proposed right in the last centuries. Okay, so and these equations, 1B's, ensure the energy conservations and also the entropy productions. And essentially, from a numerical perspective, it ensures the free energy stabilities of the systems. And as a special case, if we only have this one, right, only have the L part, the Poisson part, then it's the Hamiltonian. And if we have this, only have the dissipative part, that's basically like the phase field model. We only have the dissipations. Okay. So, but for many systems, it's basically the coupling of these two processes. Okay. And our goal is trying to construct the non-neutral fluids in terms of these variational structures. Okay. So let's take a simple example. Again, let's go back to these Hookean models. Again, it's right. It's a simple one, like the linear systems, right? And then we can show that it is actually governed by these variational structures. With this E is again the energy, that's the kinetic energy, and then S is the entropy that characterizes the systems, the configurations, the entropies, and then this L is basically the part. This is the Newtonian part, hydrodynamic part, and then we have the other part is relevant to the C, evolution C, and also similar to the M, okay, the friction matrix. Okay, so this is essentially the Hookean model. But what about the more general forms? What does it tell us? So the implication is like this. So since we assume that okay, the system, the online system, takes this variational structure, then what's the implication for the model construction? So again, we have two choices, right? So we directly construct the PD forms or the variational form. But the problem with the PD form is that if we directly construct the model in these PD forms, the intrinsic variational structure could be very easily violated. And then as a result, right, if we try to directly fit with the right-hand side, it's almost, I would say, mission impossible to exactly ensure that the right-hand side admit a energy variational structure. It's just like you think about if you have a vector valued function, you want to learn it, but you know that this is from it's a force, it's a gradient of a potential function. If we directly fit the force term, you cannot guarantee that it is the gradient of of a potential function. That's essentially the similar ideas. So that's why we propose that instead of fitting the PDE, we're going to construct the variational structures. Okay, so I know this is a little bit heavy, but I'm going to just focus on the main ideas. So as we mentioned earlier, we're going to introduce a set of generalized configurations, C, right? And this C will be used to capture the polymer configuration, which is essentially the entropy forms. Then, accordingly, we're going to modify this friction matrix, friction operators, in these generalized forms. And specifically, this term is the symmetrical part, which will be used, okay, to construct the constitutive dynamics, okay? And this one, the second part is the antisymmetrical part, which will be used to construct the object tensor derivatives. And essentially, we're going to establish a joint learning of the C, okay, and these variational structures for these entropies, the M, rather than the PD form. Okay, so that's the rough ideas. Okay, I've skipped some details. And to proceed, one very important mathematical constraint is that we need to ensure, right, this one, that ensures the energy conservation, the entropy production, right? So we need to ensure this condition. So again, I'm going to skip the details, but just to show you that the following, we propose these structures, and this structure will strictly satisfy these degeneracy conditions. Okay, so in other words, that boils down to construct the M, it boils down to construct this one, the component M42, 43, okay, in this one. And in particular, this 42 will be constructed taking these forms, while E is based on fourth order tensors. Okay, take this one. And okay, so if you trust me that these structures satisfy this degeneracy condition, we can proceed, and then we can derive the PDE forms from this variation, generalized variation structure, and the constitutive dynamics for individual C will take these forms. Okay, now we get the PDE forms. Okay, it is derived from the variational structure. Go ahead.
Are you learning the form of DC, DT? You said you had many choices there.
Yes.
Are you taking one, or are you going to learn?
I'm going to learn it. I'm going to learn it from the micro scales.
And is that clear from the structure here? How did the
This is a placeholder, right? This is a it's just the basic fourth order tensors. Yeah, we just propose that these forms will ensure this degeneracy condition. But so far, I have not talked about how we're going to learn this from the micro scales. Okay, sure. Okay, so anyway, again, so we start from this generalized variation forms, then we can derive the PDE forms, okay, which takes this one, and also it gives us the closures for the polymer stress, okay, which takes this one. Okay, now, this gives us the variation forms and the PDEs. Then the question is how we're going to learn the individual term, or how do you represent these individual terms that preserve the physical constraint and micromodal fidelity? So that's the next question, right? So as a summaries, okay, so what we have is that we propose a different pathway to learn this. It's kind of like I think we briefly discussed like this before. It's kind of like this. Let's say we want to have a horse-drawn carriage from San Francisco to Los Angeles, right? So what do? We have two choices. One choice is that we'll train the PD. It's kind of like we train the horse to be very super smart, that he can find his way, right, from San Francisco to Los Angeles. But the other way, alternative way is like this. We build a track between the two cities and ensure that this carriage always run on this track. And the variational structure is essentially the track we are building. Okay? So with that, let's proceed to the next one. Now, we propose that we have this track. So the next task is then how we're going to build the neural network representation for this variational structure. So essentially, we need to ensure that the macro models, okay, we need to satisfy the framing difference. Okay, also ensure that this one is the friction operator is positive definite, and also you need to ensure that the entropy is concave with a specific equilibrium state. Okay, and also we need to ensure that if the conformation tensor is positive, then it should remain positive as the system evolves. Okay, so I think we can skip some details. Okay, first we're gonna start with the entropies. The entropy needs to be concave, and the framing difference. So we propose that we're gonna construct the entropies in terms of this matrix invariant, okay, like this one. And then we can modify the basic structure of convex input neural network to construct this the entropies, okay? So next one, okay, is about the equilibrium condition. I think I can skip this. It's just Now, the next one is the friction matrix. The friction matrix needs to be symmetrical positive definite and the framing difference, especially needs to be commutable with C. And because of this constraint, we propose that we're going to represent the friction matrix by the polynomial basis, okay, the C. And furthermore, because of the Clay-Hamiltonian theorems, we note that the higher order, the matrix, the polynomials can be determined by these low orders. So therefore, we can just take these low order forms to represent the high order polynomials. And because of these observations, we propose that we can represent, okay, the friction matrix by this polynomial basis. Okay, essentially, okay, so this is the final result. We're going to represent the friction matrix, take these forms where this W is just a set of polynomial bases, and the gamma will be the coefficient matrix that will be learned. Okay. So, and then we can show that, mathematically we can show that it satisfied all this constraint, okay? And similarly, we're gonna deal with this object tensor derivatives and it takes similar structures, okay? And now we also show that this is the system also ensure the positive preserving dynamics, okay? So essentially, if we assume that the entropies take these formulations and assume that all the individual terms is bounded, then we can show that if the dynamics, okay, the C conformation test started with positive, okay, then it remains positive. Okay, I'm gonna skip the details for the proof. Okay. Okay, now we have the energy variational structures, and then we also have the symmetry preserving the neural network representation. So the last step is trying to learn all these macro models from the micro scales. Okay, so how we're gonna pass the physical laws, okay, from the micro scales to the macros. So, okay, let's go back to this one. Earlier we proposed that we're gonna learn a set of features, right, encoders to encode the polymer configurations and as the generalized conformation tensors. So the question is how we're gonna pass the physical, okay, the physical law across it. So here, one important observation is that, okay, we only need to close the polymer stress tau p, okay, and its own constitutive dynamics. The polymer configuration, this high dimension PDF function, is a sufficient condition, but it's not a necessary condition. If we know the high dimension PDF, okay, it's good. We know everything. But on the other hand, it's sufficient, but it's not required for us to close this tau p. Essentially, we can establish joint learning, okay, for all these features, okay, this B and the representation, okay, of the tau p, the polymer stress, and the constitutive dynamics. Okay, so in other words, we can skip, okay, we can give up the direct approximation of the PDF by establishing direct learning of the encoders that matches, okay, the polymer stress and the constitutive dynamics. So that's the key observation here. We give up the direct approximation of the high dimension PDF. So that's the key. And actually this one is enable us to help us to deal with the high dimensional problem without the computational complexity. So that's the key. So to proceed, first we need to build this the symmetry preserving encoders, right? For this. So here we started with the downbound molecules. So to preserve the symmetries, okay, if let's say suppose that the encoders is a vectors, but if it's a vectors, then it's need to satisfy this constraint. If on the micro scales, if the polymer has rotations, the output, okay, this B will also have the rotation accordingly. But if this is true, then we can show that these encoders must take this form. Okay, we can show that it must take this form. But if this is true, then by taking the average, it gives us the trivial result. So that's not possible. So the next choice, okay, would be taking the tensor rather than the vector. But if the tensor is not to satisfy this constraint, and the simple non-trivial choice would be like this, B as F and F transpose, and F is a vector. But if F is a vector, as we show here, it must take this form. So that's just a simple choice for the encoder function, symmetry preserving encoders. Okay, so similarly, we can also design the symmetry preserving, okay, encoders for arbitrary structure, more complex molecules. But I think I should skip this one and go to the how to close the constitutive closure for H and also the object tensor DCDT as case asked, right? So how we're gonna close this system without using the time series. Recall that for this DCDT is not unique, and also for the H, the constitutive closures, it must satisfy this framing different constraint. So how do we gonna learn this from a micro scales without using time series samples? So to answer these questions, essentially, is ask where we can transfer it to ask this question. Giving a snapshot around the micro scales, okay, would it be possible to determine the following dynamics, okay, without using the time series? Is it possible? Intuitively, the answer is no. If we directly learn the dynamics as a black box, right? If we treat it like a black box, then we have some snapshot. We are not able to learn the following dynamics because we have to rely on some time series to infer the dynamics. However, the answer is yes, if we are able to explicitly use some micro-scale physical laws on the micro scale. So for example, if we know that on the micro scales, the system, let's say, is governed by this very simple, let's say, over-damping Langevin dynamics, then if we know this is true, in particular, if we can utilize this V, the micro-scale potentials, then we should be able to directly infer the macro-scale dynamics from a simple snapshot without using the time series. So that's the key. Okay? The key is to utilize the micro-scale physical law rather than treat it like a black box. So can we do this? The answer is yes. Recall that we have proposed to establish a set of encoder, right, as a placeholders to represent the polymer features, right? Since we have established this micro-macro correspondence, then we should be able to derive their evolutions from the Fock-Planck equation, okay? And the Fock-Planck essentially carries, right, the micro-scale physical law. And in particular, we can derive, right, that time evolutions of the C's, okay, from the Fock-Planck equation that takes this equation 2. Okay, you don't need to worry about this equation, but the main point is like this. All the micro-scale physical laws, right, the molecular structures and the potentials can be automatically encoded into these equations. And we can further show that this equation 2, derived from Fock-Planck equations, strictly preserve the Fermi difference constraint. Okay, again, you don't. So here's the logic. Yeah, you don't need to worry about the equation, the detailed form. But here the logic is like this: we propose to a set of encoders, right, from microscale B to C, and then since we have these encoders as placeholders, then we can derive their corresponding dynamics of C from the microscale Fock-Planck equation, and this enables us to directly encode the polymer stress and the potential function. So that's the key. And furthermore, we can show that equation 2 strictly preserves the Fermi difference constraint. So I'm going to skip the details, but just show you the left-hand side. These two terms, okay, within two frames, while the second one is rotating with respect to the first one. So the left-hand side, these two terms will take these forms, okay, in these two frames. And then a very interesting observation is like this. If we combine these two terms together, you can see that these two terms together will satisfy this Fermi difference constraint. Okay? So what does it mean? That's exactly answer Keith's question. Do we learn it from microscale? Yes, because these two terms together satisfy the Fermi difference constraint. So it means that it provides us a microscale definition of the object tensor derivative. That's exactly the terms, the operators we're looking for. Okay, so we don't need to guess does it look like on the macro scales. We can directly learn it from the micro scales, and we can ensure that this satisfies the Fermi difference constraint. So that's the key point. Okay, so okay, I think I'm gonna try to finish in a few minutes. So let's put everything together. We start from a variationally formed models for the non-Newtonian fluids, right? We start with the field variables and the E, energy, entropy, and also the variation structure. Then we can get the PDEs. And then to construct it, we can directly learn these neural network representations by matching their microscale correspondence terms, right? That we can collect it from the microscale samples. And in particular, you can see that all these individual terms, their corresponding terms does not rely on the time derivatives. Everything is just from the time discrete samples. That's very important, okay? Because we utilize the microscale physical law. So you can see, okay, we can just collect the discrete samples, right? So that's the key. So, okay, so I think we should skip this. Just we'll collect the discrete samples. And we're going to establish a joint learning of both the encoders and their corresponding this variational structure, okay, by matching this one. This is essential joint learnings. Okay. And so to just recall the challenge we discussed earlier, right? The trainings only relies on the discrete samples. That's essentially challenge 1. And we enable the analytical forms of the macroscale physical laws, okay, pass across the scales. And this variation structure ensure the energy stability, okay, on the discrete levels. So I'm just giving, I think the audience is not really, about the numerical PDE, I just give one example, right? So since we have these energy variational structures, then it's very easy to develop all different numerical schemes that ensure the stability. So here I just pick one common one, like the scalar auxiliary variables, right? this is just standard way to ensure the energy stabilities, right? To ensure some auxiliary variables, and then it's very easy to design this numerical scheme. But as maybe Keith, you don't like these schemes. If you don't like it, okay, I know you don't like it, and then, yeah, you can choose your own favorite, your own numerical scheme, right? To discrete, you don't need to stay with this SAV scheme. But the main point is like the PDs take the model we have, right, has an inherent energy variation structure. That's the key. Because of this structure, then you can utilize the structure, develop your own numerical schemes, okay? Okay, so I think we should skip the numerical examples. I just show you that we have the dumbbells, right? This is well known is a challenging problem. There's no closed systems because the potential is diverged. And here just some numerical results. We can show that our models, the blue ones agree well with the red one, the MD ones, while the conventional closures, right, show the large deviations. And this is the object test derivative. It's very important to capture this derivative, object derivative from microcell, otherwise we have the large deviations. And here is just the entropy and free energy. Okay, so different molecule structures, I think we should skip. Here we can also capture the hysteresis loop, the memory effect. Okay, and if we just choose this one, the simple one, like the hooking or P, you are not able to capture this the hysteresis loop. Okay, so finally, it's about some 2D examples. We can also capture it very accurately. Okay, so for the summary, I think we talked a lot about what the model can do, but actually what I want to emphasize is what we have does not, okay? Instead of saying what it does, I want to say what does not. So I want to emphasize that this machine learning model does not just learn a black box from the time series sample. We do not do this. And we do not rely on this empirical choice of the constitutive closure. And also, from a numerical perspective, we do not seek the direct approximation of high-dimension PDF. So that's the key. We do not do all this. And that's something very common in the current machine learning-based approach. And we do not do that. Okay? So, open problem. So since this workshop is mainly about the charge fluid, I think the framework I introduced here is closely related. If, for example, so if the mean field approximation for the Poisson-Boltzmann or the PMP equation, right, can fail, we have learned from many very nice talks from the early morning and the previous days, right? So there's some correlation. In fact, would it be possible, okay, to introduce this correlation effect to both the energy function and also the dissipative process, right? So that will help us to capture both the equilibrium and the transport process, okay, beyond the mean field approximation. I think that could be very interesting to capture some of the system far from equilibrium or the interface. So that's something, okay. And also, from a numerical perspective, is there any way to improve the semi-supervised learning? Okay, so that's something we should keep in mind. Okay, so I think I should stop here, some references, okay. And yeah, thank you.